Okay, today we are going to address a fairly simple problem involving two boxes on a table, and we are applying a force to this box, which we'll call force F. Very creative naming. So we have force F, and that's applied to box number 1, which is 73 kilograms, which is in contact with box number 2, which is 104 kilograms. And this force has a size of 729 newtons. One of the things that's really important for us is that we're looking for the acceleration of the system. So I'm just going to go ahead and write that over here, just so that I don't lose sight of what we're looking for. We're also told that the coefficient of friction between the boxes and the table is 0.15. And this is actually very important because it makes the problem much simpler than if each box interacted differently with the tabletop. So what I'm going to do is I'm going to just do some arrows over this way, and we're going to look at this as a system. We would still look at it as a system even if each box interacted differently with the table, but it just makes it a lot easier to draw it out and to combine it as a system when everything is really acting in a similar fashion. So here's my object. These are my two boxes. And I'm going to draw some forces, first of all, vertically. And we have a force of gravity downwards. Whoops. That doesn't look too good. We have a force of gravity downwards. I'm going to make this the negative direction, and we have a normal force upwards. Now, while these do not have to be equal but opposite to each other, in this case it's a pretty fair bet because gravity is really the only force acting downwards, so the table only has to act against gravity. And I'll go ahead and label this as the positive axis. The next forces that we're going to look at are the horizontal ones. So we have the force of the push this way, and we have a presumably smaller force of friction in the other direction. If the force of friction wasn't smaller, then we wouldn't get any acceleration, and that wouldn't make for a very interesting problem. And I guess if I'm being consistent, I ought to label this one as positive and this one as negative axis direction. So now I'm just going to go through and list my givens for my system. I have, first of all, I have the mass 1. So mass 1 is 73 kilograms. I have mass 2, which is 104 kilograms. I have the force, which is 729 newtons. There's also a coefficient of friction. So I have the coefficient of friction, which is 0.15. And I believe that's about it. The only other thing that I'm going to say is that the acceleration vertically is going to be 0 meters per second squared. And the acceleration in the x direction is the thing that we're ultimately trying to find. Now, one of the things that I'm going to do is I'm going to start off actually looking at the vertical direction. And the reason I'm going to do that is because I know what the answer is going to look like. I know because of what friction is, friction being the coefficient of friction times the normal force, I'm going to first off need to figure out what is the normal force. So I'm going to start off with the sum of forces in the y, and this is something that you'll get used to doing. Even though you're interested in what's happening horizontally, sometimes you need to figure out what's going on vertically first. So I have the mass times the acceleration in the y direction, and that just goes away and becomes 0. So now the next thing that I have to do is focus in on what forces are acting vertically. And because I drew my meticulously crafted diagram, I have no questions about this. I have a normal force, and I have a force of gravity. And the fact that these are the only two forces and they're equaling 0 confirms my initial suspicion that the normal force is just going to be the same as gravity, but in the opposite direction. Force of gravity is, because I identify this as the negative direction, the force of gravity is going to be equal to a negative number, and then the normal force will be equal to positive mg. I'm not sure how yellow is going to look, but I'm going to try it. So then the next thing that we'll do is we'll focus in on our real goal, which was to figure out what the acceleration was in the x direction. So I first off need to figure out, well, what forces am I looking at? I'm looking at F, the force of the push, and I'm looking at the force of friction. And I can just draw this information from my diagram, m times a. Well, this force we know already, so that's easy. I'll just leave that alone. But this force of friction, it's in the negative direction, which means it's going to be equal to a negative number. So I have the opposite of mu times the absolute value of the normal force, because we don't want the direction of the normal force making a difference as far as our force of friction goes, equals m times a. And then I just take this over here and plug it in for the normal force. So I have force of push minus mu mg equals m times a. And then the last thing I'm going to do before I start substituting some things in is divide by the mass. So I have F minus mu mg divided by mass equals the acceleration. Now, one of the key points here is that this mass is not the mass of box 1, it's not the mass of box 2, it's both masses. So I'm going to say F minus mu times m1 plus m2 times g divided by m1 plus m2 is equal to a. And now all I need to do is plug in my numbers and solve. So I'm going to have, and I'm actually going to do it in a different color just because I don't really like the yellow too much. So I'm going to have 729 minus 0.15 times the total mass, which is really just 177 times 9.8 divided by the total mass of 177, and that gives us a total acceleration of 2.65. I'll just write it down here, 2.65 meters per second squared. And that's just about it for this problem. There's only one other thing that we might be able to look at. You have another problem related to this one, which is find the force that acts between the boxes. For that, actually I think I'm going to push that off to another related problem, because I don't think we quite have time now that I'm looking at that more carefully. Alright, that's it then.